Hello guys, my name is Earl Soriano from 12 STEM 2A, and I will be discussing the combination of resistors, specifically the series combination. So let's get started. Individual resistors can be connected together in either a series connection, a parallel connection, or combinations of both series and parallel to produce more complex resistor networks whose equivalent resistance is the mathematical combination of the individual resistors connected together. A resistor is not only a fundamental electronic component that can be used to convert a voltage to a current or a current to a voltage, but by correctly adjusting its value, a different weighting can be placed onto the converted current and or the voltage, allowing it to be used in voltage reference circuits and applications. Resistors in series or complicated resistor networks can be placed by one single equivalent resistor or impedance, and no matter what the combination or complexity of the resistor network is, all resistors obey the same basic rules as defined by the Ohm's law. George Simon Ohm showed that relationship between voltage, current, and resistance formulated the Ohm's law. This law is the basis of electricity. For more clarity, here's the Ohm's law, the triangle that will help you analyze easily the law. It shows here that if we're looking for the voltage of an electrical circuit, this is the formula that we can use, which is the voltage is equal to the current multiplied by the resistance. If we are looking for the current, this is the formula, which is the current is equal to the voltage divided by the resistance. And if we are looking for the resistance is equal to the voltage divided by the current. The law states that the voltage is equal to the current multiplied by the resistance, where the voltage is in volts, the current is in amperes, and the resistance is in ohms. Resistors are said to be connected in series when they are daisy chained together in a single line. Since all the current flowing through the first resistor has no other way to go to, it must also pass to the second resistor and the third, and so on. Each of the electrical devices in this circuit diagram are represented in symbols. Resistors are represented by zigzag lines, while the two vertical lines, the short line and the long line, represents the battery. And now, let's focus on the characteristics of the resistor in series combination. If different resistance are joined with each other such that there is only one path for the flow of electric current, then the combination of such resistance is called series combination. In series circuit, electrons travels on one path. So if one resistor is broken or any fault occurs, the entire circuit is turned off. Some Christmas tree lights can be in series circuits. If one bulb goes off, the entire string goes out. Now, let's focus on the ways of how to identify the equivalent resistance, current, and the potential difference of a circuit in series connection. First, the equivalent resistance. As the resistors are connected together in series, the same current passes through each resistor in the chain, and the total resistance of the circuit must be equal to the sum of all the individual resistors added together. The total equivalent resistance is therefore given as the sum of the all resistance in the series connection. For the current, all the current flowing through the first resistor has no other way to go to. It must also pass to the second resistor and the third, and so on. So the amount of the current that flows through a set of resistors in series will be the same at all points in a series network. That is why here in our formula, the current of a series circuit is equal to the current of each resistor that are connected in the circuit. So, for finding the current of a series connection, here is the formula from the Ohm's law. Current, which is represented as letter I, is equal to the voltage divided by the resistance. And for the voltage across each resistor connected in series follows different rules to the series current, We know from circuit that the total supply of voltage across the resistors is equal to the sum of the potential differences across resistor 1, resistor 2, and resistor 3. Using Ohm's law, the voltage across the individual resistors can be calculated as the voltage is equal to the current multiplied by the resistance. And we can also use this formula. Here are some sample problems of a series circuit. Example circuit number 1. Using Ohm's law, calculate the equivalent series resistance, the series current, and the voltage for each resistor in the following resistors in series circuit. The given resistance in this example are 1000 ohms, 2000 ohms, and 6000 ohms. And for the voltage is 9 volts. We will calculate first the equivalent resistance because we need it for the solving the current later. The formula that we will be using is this. Next, we will substitute the given resistance to this formula. And now we can calculate it. 1000 ohms plus 2000 ohms plus 6000 ohms will be equal to 9000 ohms. So our equivalent resistance is 9000 ohms. Next thing that we will solve is the current. Since I said earlier that the current of a series circuit is equal to the current of each resistor that are connected to the circuit, the formula that we were going to use is this, which is the current is equal to the voltage times the equivalent resistance. First, we will substitute the given voltage and the equivalent resistance that we solved earlier to find the current, and then calculate it. The current of this example circuit is 0.001 amperes or 1 milliamperes. The last thing that we are going to solve on this series circuit are the potential differences of each resistors on this circuit. We can find the potential differences of the resistance 1 by multiplying the resistance of the resistor 1 to the current that we solved earlier. Substitute the given and then calculate it. So we got 1 volts on the potential difference of resistance 1, 2 volts for the resistance 2, and 6 volts for the resistance 3. We can prove the potential difference if it's aligned to the given voltage of the example by adding all the potential differences of the resistors, and we got the same voltage, which is 9 volts. Here is our example series circuit number 2. We will use the same procedure we used to solve the example number 1. First, the equivalent resistance. Here is the formula. Substitute the given, and here's the equivalent resistance of the example series number 2, which is 60 ohms. Next is the current. Use again the formula. Substitute the given voltage and the equivalent resistance that we got and calculate it. Here is our final answer, which is 0.2 amperes or 200 milliamperes. Last, the potential difference. Using this formula, substitute the given current and the resistance. Same thing on the resistor 2 and resistor 3. And here are the potential difference of each resistor in the series circuit. Proving it will determine if we got the right potential differences of each resistor. And that's it. Thank you for watching this video lesson. I hope you all learned on this lesson.